Hey, my name is Gilberto Feliu and my faculty advisor is Dr. Ron Zhang. My project is called Artificial Intelligence Powered Autonomous and Distributed Multi-Drone Platform. This work combines gazebo simulation and ROS-based multi-UAV coordination, RGBD perception, and deep Q learning. Three simulated F450 drones search for 25 target disks placed in clustered regions of the field. And the objective is not simply to fly three drones. The objective is to create a pipeline where the drones scan the environment, build a target map, and use a learned policy to decide where the drones should be placed for better coverage. The current validation result is 23 out of 25 disks covered, or 92%. That gives us a realistic baseline for improving the system with live perception and replanning. Now, this slide shows how the search environment and the initial coverage strategy are defined. The target disks are placed in clustered regions rather than evenly across the field. This matters because clustered targets create coverage gaps and make placement decisions more meaningful. The search area is divided among the three UAVs. UAV scans the center region, UAV 2 scans the left region, and UAV 3 scans the right region. Each drone follows vertical serpentine passes through its assigned area. The sweep generator creates a structured path with repeated lanes instead of random motion. This makes the experiment repeatable, which matters to us. If the layout, trajectory, or policy changes, we can compare coverage results under the same search conditions. After the sweep, the system uses the target information to choose drone placements that maximize the number of covered disks while reducing unnecessary overlap. And this slide shows the perception pipeline from simulation to the world frame target map. The first panel is gazebo. This is where the drone's terrain and cluster disks exist in the simulation world. The target disks are visible and placed at known world coordinates. The second panel is RViz. RViz displays the planned trajectories, vehicle state, and sweep coverage. It's important to also notice or to also mention that it is useful for verifying that the three drones are actually scanning their assigned sectors. The third panel is the detection stage. Each drone publishes a front-pitched RGBD camera feed on its own ROS2 topic. The coordination node subscribes to the matching topic for that UAV. The perception pipeline is designed to support YOLO detection. For the current gazebo targets, the live scan also uses red and gray color and shape filtering to verify that the full detection to coordinate pipeline is functioning. With that being said, unique detections are merged into a world frame disk map instead of repeatedly counting the same disk. And here we go more into the deep Q learning placement policy. The current offline policy treats drone placement as an RL problem. The environment contains 25 fixed disk positions, 3 drones, and a grid of possible placement cells. The state represents the current placement configuration and target layout. The action selects the next grid cell for each drone. The reward is based mainly on how many disks fall within the coverage radius of at least one UAV. The reward can also penalize overlap and remaining coverage gaps, which comes to be important. The DQN trains offline using epsilon greedy exploration. Early in training, the agent explores different placements, and as training progresses, it increasingly uses actions with higher predicted reward. Replay sampling and a target network are then used to make training more stable. And with all of this being mentioned, the saved policy provides an ideal layout benchmark. The adaptive extension will use the live disk map from the sweep to update placement decisions during operation. Now, this slide shows the live runtime interface. The terminal shows ROS coordination messages and service calls. The system sends commands to UAV1, UAV2, and UAV3 through the MRS control interface. Arvis shows the planned sweep and vehicle state. Gazebo shows the drone positions in the simulated world, and the lower camera windows show the synchronized RGBD feeds from the front pitched cameras. And I should also mention that a key runtime correction was fixing the camera subscriptions. Each coordinate node now uses its configured RGBD topic, such as the front pitched camera topic, for its own UAV. Without that correction, the detection could be running while listening to the wrong image stream. And the scan logic was also changed so the drones do not permanently stop after the first target. In scan mode, the system continues the trajectory and records unique disk observations for the map. Now, this slide shows the coverage validation snapshot. The colored circles represent the coverage regions of the 3 UAV placements. Green points are disks covered by at least one UAV. The red outline points are the 2 disks that remain uncovered. And for this validation, a 2-meter position offset was applied to one UAV placement. The result was 23 out of 25 disks covered, which is 92% coverage. This result is important because it is more realistic than only showing the ideal offline result. In a real deployment, localization error, trajectory tracking error, and imperfect detections can shift the UAV away from its planned position. The saved offline policy still achieves 25 out of 25 disks in the ideal fixed layout benchmark. The difference between the 25 out of the 25 and 23 out of 25 is the motivation for adaptive replanning. Now, the main contribution of this project is the integrated platform. The system already includes a 3 UAV MRS and gazebo environment, a clustered target generation, sector-based sweep trajectories, ROS control commands, RVIS visualization, front-pitched RGBD camera feeds, and an offline DQN coverage policy. The project also now has a clear connection between perception and planning. The scan can detect and merge unique target observations instead of treating the first detection as the end of the mission. The next technical milestone is to validate detection consistently across live simulated frames and maintain an accurate world frame disk map while the drones are moving. After that, the updated map can be passed to the placement policy so the system can choose adaptive actions rather than relying only on the original fixed target layout. Future evaluation will measure coverage percentage, time to detection, duplicate detections, and replanning performance across repeated trials. Nonetheless, to conclude, this project connects multi-drone simulation, perception, and learned coverage placement in one platform. The current system establishes the simulation, coordination, scanning, and offline policy baseline. The next step is to use reliable live target mapping to drive adaptive replanning. All right, that's everything, and thank you for watching.